Afternoon, ladies and gentlemen. Welcome back. Final session. We're a little thin on the ground, but I'm hoping we'll get a few more people back from coffee as we go through the session. Arthur's pointed out everything is recorded, so hopefully we can catch up for those who don't catch everything. Same format as the previous panels. We have 15 minutes and 10-minute sessions. We're going back from having looked at some closure and rehabilitation aspects of mining. We're going back and re-exploring some innovation and also looking back at some of the critical mineral aspects. We've got 7 speakers. We've got just over an hour and 20, I think, to fit it all in. And then obviously we have the Deputy Minister closing, so we can't run over time too much. All the speakers will do as we've done previously, come up to the stage and sit down. I'm hoping we will have 5 or 10 minutes for questions at the end. The only exception to that is Christian, who's our first speaker. Unfortunately, he has a plane to catch. So if you have any burning questions for Christian when he has finished, we'll take 1 or 2 questions very quickly from the floor. Otherwise, we'll try and get a discussion going at the end. So I guess without further ado, we'll move straight on to Christian's presentation. Christian is going to look back. We've talked a little bit about it already, but obviously critical minerals are very important in the defense industry. And we've heard over the last day and a half issues arising and how we fund some of this, particularly in the European context, and some contrasts have been made with how this is being dealt with in the US. But looking forward to Christian's presentation, and Christian, feel free to add some color based on the discussions we had just before the start.
Great. Thanks for having the opportunity to talk about defensive raw materials and from a light of a processing engineer. First, I have to admit I'm not a processing engineer. It's just a couple of processing engineers that are working together with me, and I'm here to represent their view. So I want to talk about defensive raw materials, also highlighting why they are critical, and then giving you 3 case studies. The case studies will mainly be about rare earths, it will be about tungsten, it will be about graphite. But please let me go into first introducing the company. So Dolphin Anserplan GmbH is a German process development, process engineering and consultancy company that concentrates on engineering services on specialty industrial minerals and critical raw materials projects. We do process development, process engineering, so flow sheet design, operate piloting facilities, and come forward with PEA, scoping studies, PFS, and FS study solutions. And we are doing this in the field of the renewable energy, electromobility, but also in the defense sector where my talk's about, and the commodities we are covering inside the companies: lithium, graphite, cobalt, rare earths, high purity quartz, and tungsten. So let me jump into and give you at least a little bit of the German view about this. So there are 34 critical elements listed on the EU list. Some of them are highlighted on the right-hand side. And it's not about that all the mining is done in China, but most of the processing is really done in China. And on the right-hand side, you see the dependency of there. On top of this dependency on China is that the just recent geopolitical tensions forced China to put export restrictions in place that not only sanctions the minerals, but also the technology to work with these. And these are especially the minerals I want to talk about. So graphite, tungsten, as well as rare earths. There were some sanctions put in place by the end of the last year, or even 2 weeks ago. And these are affecting heavily German industry and the defense industry. And these export restriction ties especially down for defensive raw materials, because it is definitely said that military purpose needs a special requirement, a special permission from the Chinese government to overforce it. On top of this, what we hear in here a lot is stockpiling might be a measure to deal with this. Stockpiling is expressis verbis prohibited by this. So if you want to stockpile some rare earths, you don't get them out of China. So find a different solution. We are happy to deal with this, and I want to start with the case studies. The case studies I would like to present are always in the same way. I show you the military applications where these commodities tie into, and then the view of a processing engineer, what we are facing and what problems we have solved dealing with these commodities in prior projects. So you start with the rare earths. We all know what rare earths are about, but where are they in military applications? So generally speaking, anywhere you find a motor, there will be rare earths, but there will be also other applications, such in optical laser. So you got some neodymium, europium doping there, but also into electronic warfare or radar and sonar systems. Rare earths playing an essential role. So these are the weapon systems or the defense systems that are affected with the ban of the rare earth systems. I think it's pretty essential, but then what does rare earth projects make it so special? If you look on the left-hand side, there's a breakdown of the deposits that are pretty well known. So you're on the top, you have the two big Chinese deposits, Bionoble, probably the biggest rare earth deposit on the world. Then you got Longan, you got Linus on the bottom, and you got Mountain Pass. What I try to highlight is the light rare earths, which are essential for magnets, and the heavy rare earths, which are essential there. Basically, you don't see any deposit that is quite similar. So if you want to substitute Bionobo, Mountain Pass won't do that because you're missing probably the heavy rare earths portion significantly there, and also the cheap rare earths such as yttrium, lanthanum, and cerium are very heavy overrepresented in Mountain Pass. Also, if you have a Longan type deposit, it won't probably help you if you want to go into magnet production because it just don't have any light rare earth elements in there. So you have to put a special emphasis on what do I want to do with that deposit when looking for. Also, when I have a deposit, which application do I target in my marketing? And then a good friend of mine who's a mineralogist, he likes our rare earth deposits because rare earths come with 200 different minerals. Long story short, the mineralogy of these deposits basically dictates the whole thing about this. And it could be really from a caustic leaching towards acid pressure leaching, towards caustic baking, high pressure leaching, whatever you want. It just depends on the mineral suit that you're having. And on top of this, it's not just the mineral suit, it's also the mineralogy of the side minerals. If you have some fluorine with your deposit, they will form in situ in a leaching process rare earth fluorides, which is hardly soluble, so good luck with this. So you have to have good fluoride flotation to get them off. So if you want to have challenging deposits, just go into rare earths and enjoy them. If you want to have something other interesting, it might be tungsten. Where do we need tungsten? Tungsten is in the mix. I think it was mentioned Tungsten West, a significant tungsten deposit that is sitting in the UK. It's currently under, or the US is eyeballing heavily for this because armor-piercing ammunition and weapons will be constructed using tungsten, and also armor plates and high-temperature steels you use for rockets or fighter planes will require the tungsten. But a tungsten deposit is not a tungsten deposit. The two main minerals in the tungsten world is the scheelite as well as the wolframite, and these minerals are totally different. These minerals, so the processing scheme of either of these minerals is so different that you can rule out just by a simple mineralogy a complete scheme or a complete set of processing variants from the very beginning would be pretty easy, but they come together. They always come together. You'll have always this mixture series. And then grade comes in. And I think tungsten is one of the few critical raw materials where grade is really king, because if you have too low grade deposits, you have to go into autoclave leaching. On a higher grade deposits, you have a caustic leaching process, but if it comes to lower grades, you go into autoclave, you need higher temperatures with this, so your capex will also improve. So this is one of the few examples where I really confess to grade is king on that. And then going to my very favorite and going into graphite. Graphite seems pretty easy. It's considered even an industrial mineral, and it's used in nearly any weapon system you can find. It's used in helicopters because of its lightweight. It's used in stealth application sensors because of conductivity, as a high temperature material for lubrication. Basically, it's basically dual use because simply because of the same properties it's also used in civil applications for this. And graphite's not only graphite. I know it's a mining conference, but there's also artificial graphite. And artificial graphite could not replace the natural graphite. And when you look into natural graphite, there might be vein graphite, which coming out of Sri Lanka. There are also some Namibian and Canadian vein type resources for the graphite, but the major source is really the flake graphite. And with this flake graphite, you can look at this, and I never found a deposit with a similar flake size distribution or with a similar flake size. So you can really have big, thin flakes, you can have small, thick flakes, you can have big flakes. You can do the whole iteration about this. And then also the particle size distribution of these flakes is totally different. And why is this of essence? Basically, you can break them down, so make them smaller works, make them bigger, plain doesn't work. You can't glue them together. And these flake size distributions is really dictating where is this material suitable. So your ore body dictates your later applications. So anybody that is in exploration, not only doing the head assays, but also doing maybe some MLA work on the flake sizes, or doing some flake size assay, and try to get this into your exploration program. And then when it gets to purity, typically graphite is done to a 95% purity just by flotation pretty easily. Good deposits can go up to 97%, but when it goes to 99+%, it's about the purification. You can have various routes. There's always thermal purification, there's caustic purification, always in the discussion. And the question there is not really what to use, but what's the most cost-effective route? Do I have HF available at site? Probably in Australia it might be an issue. Canada, I heard as well. Europe shouldn't be much of a problem. And when it goes about thermal, it is how cheap is my energy, and do I have cheap CO2-free energy? That would be ideal, which is not available on most of the graphite-producing countries. So it is always a trade-off to go there, and also the impurity minerals basically dictates what's the most suitable route. I hope I could show you in the remaining 12 minutes that there are some aspects you just don't see if you're talking about a rare earth deposit or a graphite deposit, but they are of essence when it comes to developing a vital, strong techno-economic process. And most of these parameters could be also tracked during exploration, doing your geological modeling, and it is maybe worthwhile considering these into your geological model. So for tungsten, maybe for rare earths, maybe include XRD data, do a mineralogy there, include this in your model, and it will help you to build a robust model. With this, I want to thank the organizers for giving me the opportunity to talk, and thank you for staying that long for the last spot. Thank you. Good.
Thanks very much, Christian. Now, I mentioned Christian does have to leave. He has a plane to catch. Is there anybody in the audience who wants to catch Christian? Do we have a question for him before he leaves? Because unfortunately, he can't join. We're not doing a formal panel session, but there will hopefully be some time for questions and answers, but Christian's the one exception. Any particular questions? I've got one, Christian, before you vanish. You mentioned Tungsten West. Obviously, you've also mentioned that the US are looking at it. I think somebody mentioned this morning the Japanese are looking at it. Yeah. The question is, I know this isn't a process question, but we're here to look at security of supply. Why aren't the Europeans investing? It's in the UK. I know we're not mentioning the B word, but
I think it's my take. I think the Europeans are risk averse, and I think they want to pick a winner, and they are not sure if Tungsten West would be a winner, and the US is just faster and takes the risk. That's my take.
Thank you. Thanks very much, Christian.
Thank you.
Have a good flight. Thanks. So we'll move on now, and the next one we're going to hear from Frank from SLR. Title of his talk is Innovation Across the Mining Cycle, Tackling European Raw Material Challenges. That's quite a big ask in 15 minutes. But yeah, looking forward to it. Frank, it's all yours.
Cheers, John. Thank you. And good afternoon, everyone. So yeah, I'm really going to focus my talk on examples of innovation. SLR has recently expanded its capability in Europe with the acquisition of Wardell Armstrong and Responsible Mining Solutions. And as a consulting business, this is where we see ourselves in the mining innovation ecosystem. There's a real hotbed of innovation happening on the left across a range of sources. And what we strive to do is match and tailor emerging techniques and technologies to real-world problems. And if we do that well, we can offer really practical and effective solutions to industry. And we think that's important. We're very aware there's a new generation of mining development happening in Europe, driven by significant forces in the world. And we have a clear overarching goal: sustainable and secure raw material supply. The part in the middle, technical project delivery, can be a long road with challenges and opportunities at each stage. So what we thought would be useful is to provide some examples from our work where innovation has provided significant cumulative value and could strengthen the delivery of the next generation of European mines. So we're going to start right at the beginning of the mining cycle. We've just made a discovery. We're part of the geology team. We're patting ourselves on the back. Funding is going to flow into the business, and we'll use it to accelerate our project through study phase and into production. That means quite soon we're going to have to grapple with the question of how much drilling is going to be sufficient to define resources and reserves and evaluate the project. And we can reframe that as what level of uncertainty and risk in our resource model is going to be acceptable. So I'll start by outlining the current approach to mineral resource estimation. We're looking at 3 level plans, so horizontal sections through our deposit. We've now done a lot more drilling. So on the left, each point is a drill hole. We log the drill hole. We have red, blue, and green rock types. We build the 3D boundaries between those rock types that control metal grade, and they're called domains. And then we use the drill hole sample grades within each domain to interpolate metal grade into our block model. And typically, we say job done. We classify our model, report resources, but we don't typically quantify the uncertainty in our model or the associated risk. And that's odd because one of the very few things that resource geologists will agree on is that that block model is wrong. It will differ to some extent from the reality in the ground. Yet the kind of status quo is to let any risk propagate through our mine planning procedures, and we'll hope for the best. This is where simulation methods could come in. They're an extension to our resource modeling toolkit. They allow us to quantify risk. So the mechanics of simulation differs in that instead of generating one block model, we're generating a range of scenarios or realizations of what the block grade could be. So each of those three models is slightly different, and the extent to which they're different allows us to calculate uncertainty. And we can map that spatially in the model on the right, where cold colors are high risk and uncertainty, and hot colors are low. At SLR, we've extended this approach to include other sources of uncertainty. So now we're simulating basically the geological interpretation, the domain boundaries. So each one of those is slightly different. And we're also simulating grade within each set of domains. And we end up with a much more complex and arguably more representative uncertainty model, where we capture the fact that there's a very high level of uncertainty in the model where domain boundaries are moving between the different scenarios. So that's sort of the theory. But what's important is, how does this add value? And the overarching answer is, this is a data-driven method that allows us to make more robust decisions. There's two main applications. One is to quantify what is the optimum drill spacing for our deposit. We do this by testing different theoretical drill grids. And we're just going to look at a domain simulation because it's nice and visual. This is based off a very tight 10 by 10 grid. We are cycling between two different scenarios, and you'll see that the domains aren't changing. The model is stable, it's therefore low risk. Contrast that with this model based on 35 by 35 meter drill spacing. The domains change dramatically between the different scenarios. This is an iron ore deposit. Red is essentially hematite ore. So this is telling us that if we're trying to mine this based on a 35-meter drill grid, we're going to have a really tough time. The red material isn't well constrained. Therefore, we're going to misclassify ore as waste, send it to the waste dump, and we'll send waste to the plant. So the kind of end point of our workflow is to test lots of these different theoretical drill grids, and we can really quantify the minimum drill spacing where the risk in our model is meeting an acceptable threshold in line with a desired resource classification. What is really powerful is then taking our uncertainty model and applying it into our mine planning process. So now we're in an underground gold case study, and we're mapping uncertainty onto our stopes. We can identify high-risk areas and de-risk them with further targeted drilling, or we can move them to the back end of our production schedule. And my final point on this is probably an obvious one, that errors in our block model can have a material impact on a project's financial performance. And this sensitivity analysis backs that up with numbers. So in the base case, where my block model is predicting a life of mine head grade of 0.6% copper, which delivers an NPV in excess of $500 million. If my model, if the production reality is a 5% drop in grade to 0.57, which doesn't feel like much, that results in an unforeseen drop of 30% in NPV. 10% drop in negative error in the grade, 60% drop in NPV. So with that context, I think there's a strong case that we could consider adding simulation to our resource estimation toolkit so we can assess risk and have the opportunity to mitigate. And the good news is, in our project here, we've done that. We've drilled our deposit to an adequate spacing. The bad news is that we've done some test work now, and the results are bad. We already knew our deposit was on the low-grade side, but we've Test work is showing it to be metallurgically complex with heterogeneous ore types. This is very much in line with global industry trends. So that begs the question, how do we turn lower grades and higher metallurgical complexity into sustainable project success? There's two pieces to the puzzle. The first is applying modern processing equipment. At the front end of our flow sheet, we can consider ore sorting techniques for early removal of waste. That means we upgrade plant feed, reduce energy consumption, water consumption, reagent consumption, and tailings volumes. One emerging example of this is the South Crofty Tin project in Cornwall, where their test work on XRT technology has shown they can remove 55% of the waste with only a 3% loss of metal. Advanced comminution speaks to energy efficient techniques like high pressure grinding rolls and stirred mills. These methods can optimize liberation for fine-grained ores and, again, reduce energy consumption and cost. Stirred mills, for example, are now widely implemented in the Iberian Pyrite Belt for treatment of fine-grained polymetallic ores. The last one on this slide is novel flotation and separation, and that refers to new reagents and flotation methods like stage flotation, as well as more selective collectors, which are really key when you're trying to process low-grade and complex sulfide ores. The second piece of the puzzle is how we implement those modern processing technologies. Automated and AI-driven process control is the cutting edge. This is where we are collecting real-time information from our comminution, flotation, and leaching circuits, and automatically optimizing our processing parameters. Plant audits and operational support still have a significant role to play, especially if we're adding complexity to our flow sheet. We need to be even more cautious and careful as we upscale laboratory-scale test results and design assumptions to commercial production. And the final point is flow sheet optimization. That's where everything gets brought together. And the key theme is evidence-led process design, which allows us to get the right technology implemented across the flow sheet that's really tailored to the unique characteristics of each ore body. And there's quite a lot up for grabs. We can improve metal recovery and plant throughput, reduce our energy, water, and reagent consumption, tailings volumes. We can improve our economics and resilience to variability, and more strongly align our project with EU sustainability and regulatory goals. So we've dealt with our complex metallurgy, but like any project, we're going to generate waste products. And waste can become a long-time liability if it's not proactively managed, particularly in Europe, where ESG requirements, climate pressures, and transparency expectations are intensifying. So we'll finish things off with a third case study where we look at tailing strategies for sustainable closure and ESG confidence. Waste with a purpose refers to a change in mindset. Tailings aren't waste, they're a system to be designed. And we want to shift the focus from purely containment to where we can derive value. And we'll work our way through this tailing system and highlight some examples at each stage where new approaches can enhance value. First up is the process plant, where water recovery is king. Closed-loop water circuits can improve water recovery. Less water going to tails reduces the downstream risks of the tailings material and improves the climate resilience of our operation. There may be opportunities for residual metal recovery. Benefits can include improving resource efficiency and more tightly classifying materials, by which I mean we're standardizing the physical and chemical properties, which then makes the material more amenable to safe disposal or secondary use in things like paste backfill. And finally, onto the tailings storage facility itself. Exactly how, when, and where we deposit the tails, which is depositional control, has a massive impact on remnant water recovery and facility drying trajectories, whilst climate design refers to how both deposition and drainage needs to be tolerant of climate extremes, of drought and storm events. Like anything, like most things now in mining, tailings management is going digital. We're referring to that as GIS integration, which is a facility-level platform that integrates historic data, real-time production information, and forecast information to empower operators to monitor risk and make predictive management decisions. And the higher resolution of monitoring information we're collecting naturally lends itself to better regulatory compliance. So waste with a purpose. The aim is to reduce closure cost uncertainty, improve alignment with investor and regulator expectations, and ultimately enhance ESG performance and credibility. So to try and link everything back to our session topic, to us, reimagining mining means unlocking value at every stage, from smarter exploration to cleaner processing and purpose-driven waste. Only through innovation, integration, and transparency can Europe build a raw material future that is not just independent, but truly sustainable. Thank you very much.
Thanks very much, Frank. Good insight into some of the technologies and improvements, I guess, that we can and I guess should be applying to all projects that are coming into the process or coming online, hopefully in the coming years. We've talked enough about how few there are in Europe, but hopefully we can speed that up and employ some of these technologies. The next talk is going to take a bit of a deep dive into a very specific part of the process. So we've looked at it across the mining cycle. Frank's given us an overview. Dominic from Christian Pfizer is going to take us into a specific case study looking at a particular element of the processing. So, Dominic.
Good evening, ladies and gentlemen. I think it's my challenge now to keep, at the end of the second day, with one of the last presentations, to catch somehow your attention. So this presentation is mainly referring to the comminution, especially to mills. We in Christian Pfeiffer, we have experience for more than 70 years of mill design. Myself, I have been working for Christian Pfeiffer for more than 17 years. I know many mining projects which I'm following since the beginning of my career, nearly, especially the projects in Europe. But on the other hand, the good point is there is also projects which can go quite fast-track projects, which will be maybe realized in 2 years only. And therefore, I'm mainly talking about brownfield projects. Before I will show you the 2 case studies, I will just give you a very, very rough overview about mill design. There is some key aspects like how to make the drive, how to make the bearing, the shell, and everything. And we are talking here about consumers which have a power in megawatts, with small mills with 1 megawatt, medium mills with 10 megawatts, big mills 20 megawatts or more. So I think it's worth to take a deeper view on these points. Considering the drive, when we talk about gear-driven mills, there is mainly 3 versions, and I would love now to discuss for hours about the advantages and disadvantages of every solution. Unfortunately, I have only 15 minutes. So let's go not into too much details right now. Same when it comes to motors. Again, we have three possibilities. If it's a classical slip ring motor, if a synchronous motor, asynchronous motor. And when we talk about greenfield projects, normally everything is defined in the tender coming from the consultants. Sometimes consultants it's a little bit overdone. They specify everything. They specify like it's a 20 megawatt mill, but finally, if you look at the data sheet, it's less than 1 megawatt. So it's like going to the car dealer telling, I need a car which can drive 300 kilometers per hour, I need 10 seats, I need an all-wheel drive, and finally you buy Seat Ibiza. Nothing against Seat Ibiza. Again, bearing design. 3 versions, Tronian with roller bearings, Tronian with slide bearings, shell-supported mills. So we have 3 bearing solutions, 3 drive solutions, and 3 motors. So in total, 27 configuration possibilities for a mill. All over the world, you have certain preferences. If you're in the Middle East or in America, everybody's looking for a similar version normally in a specific area. The last point, how to divide the shell and the head. It's mainly a transport issue and also for manufacturing limits. Like here in Europe, we have, when we talk about mill shells, we have 3, 4, 5 good companies who can produce such huge parts. We're talking about parts with a diameter of 10 meters. We are talking about parts with a weight of more than 100 tons sometimes. I don't know how much people really in this room have been out on a mine site, but we are talking about the clean projects, we're talking about sustainable. Finally, it's dirty, it's wet, it's dusty, and it's not clean, definitely. So we developed a very reliable, it's not working, I think. No. So one design we developed is a very special design for this very harsh conditions, for outside conditions. I don't want to go into the details, but it's special sealings on the bearings, on the gear drive, and it's a very nice solution. And this is a solution we can also very easily use for replacement of existing mills, which is coming more and more a topic for us. Because if you look into the mines, there is many processing plants with mills from the 60s, from the 70s. Sometimes maintenance was not so good, and these mills are nearly falling apart. So there is a need for a replacement of such mills. I will skip this. I have not so much time. I would go directly to one example from Brazil. I think this mill is from the 70s. It's an iron ore mine. Very old, from mechanical point of view, very damaged, nearly falling apart. What are we doing? First, we rebuilt the existing foundation, the concrete blocks. And it's not only a replacement, it's an upgrade. Because we also, then in this case, we increased the diameter to have a higher throughput. We installed the red concrete block to have an additional engine drive for more safety, for more maintenance friendly working. Then we adapted our bearings to the foundation. In this case, we even considered the existing mill drive motor because the motor is a very specific item which is still in a good condition. And finally, we have a concept where we can replace a mill, a project we can realize in a very short time without any permits. We are not touching the foundation. We're only making some small modifications. And this is really projects I like because sometimes, we are following the feasibility studies, the definitive feasibility studies, and Okay, at the end of the day, we as a company, to survive, we need not only business, we need business. So this project is really a big advantage for us. And now coming to a very new project. We just got this order at the beginning of this year in Canada. This is a SAG mill, so a semi-autogenous mill with very coarse feed size. You put in rocks with 200-300 millimeter diameter. This mill is, I would say, it's the heart of this processing plant, and it's a very unique process. It's a dry, semi-autogenous mill, where they even use hot gas for drying in this mill. And if this mill is out of operation, the complete plant can be closed. Some hundred of workers will not be able to work because the whole plant downstream side will not work. If we look at the basic numbers of this mill, for a SAG mill, it's not the biggest one with 2 megawatts. But if you stay next to such a mill with an outside diameter of nearly 10 meters and it's turning, you cannot just hear it, you can even feel it, the power. The mill is producing with 300 tons at the moment, and like very often in such cases, it's nearly falling apart. The flanges are damaged. They did several weldings. The mill shell, the gear rim, they had broken teeth. They just repaired it for a short time. So really, from the 60s, need to be replaced immediately. Looking to our scope of supply, okay, it's an optimization of the existing mill with a new mill shell, mill head, with bearings on the trunnions, inlet, outlet compartment, new liners, an engine drive which is not existing at the moment. At the moment they are using a winch to mechanically turn the mill, which is from safety point of view not the nicest way. We make an upgrade also with a sound level measurement inside the mill to know the exact filling degree. And everything is designed to be installed on the existing base frames of the old mill. So we adapt the bearings, we adapt really everything of the mill. It's a tailor-made mill only for this client. The only thing he is using, again, is the old and existing main motor. It's a synchronous motor in very good condition. They made a good maintenance, and the air clutch they have. From technical point of view, I would rather, for a new mill, I would make a medium voltage VFD instead of an air clutch, but okay. Somehow the budget was maybe also limited in this case. So on the left side, you see the 3D scan. In this case, the client ordered this 3D scan from an external company, and we got the whole 3D model, and there is plenty of equipment around the mill. And on the right side, we have our latest 3D model of the current design. If you see in violet, the existing synchronous motor, and blue, the new mill body with an engine drive. And we have now the challenge to put this piece in the big puzzle of the plant. But as I said before, we are not just changing, we are upgrading. The existing design, straight head walls, huge welded head walls, they have cracks, they have everything. We change to conical head walls, like we have in all other SAG mills nowadays. Casted head walls with 90-degree section. The gear rim, they have an asymmetrical gear rim, never seen that in another mine. And what we also do with the inclined head walls, we're also increasing the grinding volume, and we are also expecting finally an increase of throughput. Bearing design is just upgraded to this latest state-of-the-art design. Nowadays, for everything, there is a simulation. When I look at the drawings of this mill from the 1966, it's amazing what people did these days with just calculating, drawing by hand. Nowadays, we rely on simulation, but for every simulation, it's also important which parameters you use. If the parameters are wrong, the simulation is also wrong. So here it's really important to have experienced people. We have engineers which are more than 10 years in the business, who are doing this day by day and have the right know-how for such simulations. For the gear rim, we had a long discussion with the client. If helical toothing, spur teeth. Our suggestion was helical design because of reduced width, of reduced weight. Finally, the client selected a straight toothing because of he wanted to avoid the axial forces on the existing foundation. The project itself, we have in total an engineering time of 17 weeks till design freeze, and then 10 months of delivery, including also the engineering time. So quite a tough schedule, because the client is really very afraid that this mill will stop suddenly. And as I said, we are not just replacing, we are also analyzing the existing situation, the existing design. And whenever we talk about sustainability, okay, look at the mill liner. On the left picture, this is a liner plate, when it's new, 1,000 kilogram. When they scrap it, like on the picture, still more than 50%, I would say. So they scrap 500 kilos per liner plate. So what we are doing really at the moment is to analyze the wear pattern of the mill, to optimize the liners, the face angles of the lining. And also we found out with the simulation that the balls are actually not impacting on the ore, they are impacting on the liner. And imagine a 100 millimeter steel ball falling from nearly 9 meters down on a steel plate. It's a huge impact. And it's not only one steel ball, it's hundreds of steel balls, it's thousands of steel balls hammering on this liner plate. So we are just in the final design at the moment of these liners, and we expect that we will not increase only the throughput, we will also increase the lifetime of the plates. And also we are making smaller plates for easier maintenance, because imagine replacing a plate with 1,000 kilogram without any grain inside. It's a challenge. And I'm really looking forward then to the final stage of this project, when it comes to the replacement of the existing mill, because the time for the replacement is scheduled now for only 2 weeks. The discussed idea with the client is to pre-assemble the mill body, the trunnions, the head, the shell, and the gear rim. It's a piece of more than 100 tons and more than 10 meters diameter. And then they will use a gantry crane just to insert extract the existing mill, insert the new mill, and make an immediate and fast restart of this mill. So this will be then the situation when the mill is reborn, and I'm really looking forward to this very special stage of the project. Unfortunately, time is already over. Thank you very much.
Thanks, Dominic. Good insight. I guess we talked a bit about this morning about how many brownfield expansions are being looked at, and there aren't that many new projects. So you're retrofitting, improving efficiencies, particularly in Europe with high energy costs, etc., very topical. We'll move on to the next speaker now, and Esko is also going to take us into a case study. We're looking at some very specific elements of the processing. And again, very topical, we're looking at solutions to improve production and energy efficiency, which given the prices of energy in this part of the world, interested to hear how that's going to pan out. So, Esko, all yours.
Thank you, John. Ladies and gentlemen, I try to keep you awake still for a moment. I apologize because my time is so limited, so I have to go very rapidly through some slides. So I do come from Sidra, an American company behind some best available technologies for minerals processes. And those include sonotrack flow monitoring, cyclonetrack particle size measurement, and now we are introducing also P29, the separation technology that enables coarse grinding and saves up to 40% of grinding energy. So Sidra's focus is on the first grinding stages and combined classification area, because that's the area which is defining the plant throughput and has also the major effect on the recoveries, no matter whether it's question of flotation or leaching processes. So the particle size measurement cyclonetrack PSD is a step change there compared to the old conventional technologies that are having this kind of sample taking analysis from the consolidated flow over a cyclone battery overflow. And then typically old times have combined some roping detectors to monitor the cyclones, but they are not capable of measurements. So we are measuring directly from every overflow of the hydrocyclone, every hydrocyclone in a battery, 5 to 6% of the total production will be measured by our probes. And based on that, we can immediately see that how each of those cyclones is performing in the cluster, and we can drive the cyclones closer to their operational roping limit where the cut is sharpest. So we are providing the best possible particle size distribution to following stages, and we are reducing the amount of fines going back to the circulating load, so we are freeing up space for increased throughput there. So based on this, we can optimize the grinding section for the separation processes, and of course that will save some grinding energy per ton and reduce some water consumption too. Typical control circuits, perhaps I don't stay here, but if you compare the results gained by this PSD-based control, here we have a customer case that has been running for 100 days and toggling between the old system and the PSD system with 1 to 2 day intervals. And we can see that maintaining the same control targets, we are gaining much more production based on PSD-based controls. This was a copper mine case. Also here we can see that immediately when any of those cyclones go out of the targeted particle size limits, the PSD-based control is reacting to that and preventing all roping events and abnormal operations of cyclones. Then few words about such a simple thing as flow measurement. So the leading flow measurement technology has been the magnetic flow meters. They basically measure the ion flux through a magnetic field. And they are based on the assumption that the ions in the flowing material are homogeneously distributed. That's valid for the water, but not for the slurries. The slurries are having solids there, so there is always the gravity effect. There is also the mass inertia effect that is changing the ion distribution within those pipelines. It means that basically you are controlling the water, not the solids flows. And that causes quite a lot of problems on concentrators, because then you are having blockages, and it's typical concentrator loses something like 1 to 3% of production time just because of line blockages. Those are caused by the segregation of those materials, and also the air content is included there. The pumps are pumping air and losing their efficiency because of that compressibility of the air. We have developed a passive clamp-on sonar technology that measures the propagation velocity of turbulences that carry the solids forward. So it's solids flow measurement there in question. In addition to that, we can measure the volume occupied by bubbles there at that measurement position, and we can correct the errors bubbles are causing for density measurements. And you will get, of course, warnings when there are too much air in the slurry, so you can prevent the blockings. Very simple installation, just a mat we wrap around the pipe. Doesn't need any maintenance. We have had customers that have used it for 20 years, still the same performance. Some have changed the pipe under it 10 times already. No matter. Not good for our service business, but the customers are happy. Here you can see the comparison between sonar and electromagnetic technology. So it's a 3-kilometer long process line and similar meters at the both ends of the meters. And you can see how this material distribution variation is affecting to the electromagnetic flow meters. So it's a clear advantage on the control point of view. And of course, even bigger if you have magnetic materials. And here we have seen cases that the customer has been pumping air instead of slurry, so pump has lost its capacity, customer has lost something like 25% of their production there at those, and each situation has lasted hours. We can clamp on all kinds of pipes. Already 700 concentrators are utilizing this technology all over the world. Now we are introducing the P29, which is quite a step change in minerals processing efficiency, because that's a separation technology where we, instead of bubbles used in flotation, are using sponges. We just mix the sponges that are covered with the same flotation chemicals and put them into a drum with the ore and rotate that drum and capture the wanted particles there. We can do efficient separation up to 2 to 3 millimeter particles there. The porosity of the sponges will be tuned according to the particle size distribution you want to capture with these ones. The high attraction forces and tag of the polymer enables really vigorous washing for gang reaction at the early stage. So we can capture, here the dark material is the wanted material, so you see that we can capture with a very low exposure rates. So less than 1% exposure of the wanted material has to be on the particle that we can capture it. If you compare that to the same of flotation, which is 20 to 25%. So that explains that our capture is so efficient at the larger particles. The drums we call contactors, so you can put a row of those ones and control the wanted recovery to whatever level you want there by increasing the numbers of contactors there. Here we can see the example of 9 contactor rows, and you can see that still in the last one, the upgrade ratio of the material is more than 4, so there's 4 times more of the valuable materials in the concentrate than in the feed of the last stage. Basically, the process looks like this. The sponges and coarse feed are put into the contactors, and then the loaded media is washed away, and the washed material goes to the next contactor and next contactor, and all loaded media are gathered then into one tank, and there we put a biodegradable washing agent, release agent, and put it through a row of pumps that make the separation of the captured materials from the sponges, and we wash it, the filtrate through away and get the concentrate out, and the release agent is taken back, rotated to release new materials, and the sponges are fed back to capture new materials. Fast process, just 3 minutes to get a recovery over 90%. So if we can increase the grind size, so PAT value from 150 to 500 microns, you are saving 50% in grind energy. Or you can increase throughput by that same amount. Also, we are providing coarser tails, and that enhances the water recovery, even triples it. So we typically take in a brownfield case the underflow, so we take part of the circulating load and handle it with the B29 process and capture that there. And the remaining flotation there can be optimized for the fine spot better than earlier. And in greenfield projects, we can just have a crushing that goes down to 6 millimeters nowadays, and after that one HPGR, and after that B29 process. Very simple and energy efficient. Thank you for your time.
Thank you very much. I'm no process engineer, but it's the first time I've seen sponges referred to in processing. But interesting, I've obviously heard, we have talked a lot about coarse grind becoming a very useful process. We can get the recoveries up and keep the grind coarse. Yeah, I'd love to learn a bit more about that in due course, but time's against us. So Esko, thank you. We've gone from the 15 minutes down to the 10 minutes, so we're speeding things up towards the end. We're going to go back to a little bit more of innovation, and Charles, I think, is going to take us through a slightly broader approach. And just to prove that the mining industry is a small world, I discovered this morning when I met Charles for the first time that he and I grew up and went to school together about a kilometer apart, in Harare, of all places. So, yeah, if you didn't think mining was a small world, it certainly is. But I digress. Charles, it's all yours to take us through some innovation and how the Canadians are looking at innovation in mining.
All right, thank you. Yeah, it's always good to meet somebody from back home. Grew up playing a lot of rugby, cricket, and playing chess back in Zim. So anyways, everybody, thank you for staying this long. I see a lot of you here are falling asleep. So I'm going to ask everyone to do one simple little thing. Can everybody just stand up for a moment and just sit down again, get the blood flowing? Please kindly just stand up. Put your phone down for like 1 second, and then stand and sit down again. Thank you. I see some of you don't like taking instructions. That's okay. You can sit down now. Thank you. I hope that got the blood flowing a little bit. So my name, of course, is Charles Chemiranya-Beze, and I'm the VP for Business Dev and Commercialization for the Center for Excellence in Mining Innovation. And, our organization is based out of Sudbury, Ontario, Canada. And we're formed 18 years ago with the sole purpose of advancing innovation into the mining industry, and doing so in a way that ensures that mining really hits what we call the 3 Ps of mining: profitability, impact on the people, and impact on the place. Our organization is not for profit in terms of its registration with the Canadian government. And for those of you who know where Sudbury is, we are located, in the global capital of nickel. That's what we call it. Nickel City is Sudbury. We have segmented our services into 4 core areas. Number 1, innovation scouting, which means that we want to find out what innovations are out there. So if anyone here has an emerging technology for mining that they're struggling to get the mining industry to adopt, come and see us. That's what we do. we advance innovation to the mining industry. And number two, we like to find the challenges that the mining industry has. Not just the mining industry in terms of the operators, but also challenges faced by the SMEs, the METS companies, the SMBs, small to medium-sized businesses, or small to medium-sized enterprises. We like to know what the startups are facing challenges, and we also like to know what the ecosystem challenges are. So really, our approach is ecosystem-wide in terms of how we move innovation forward. And then the third thing that we do is matchmaking. That's like a dating website for innovations and solutions, innovations and services. So we try to bridge those gaps between the people that have solutions and the ones that need them. Then the fourth thing that we do really well is we do what we call commercialization services. If anyone here knows the words innovation valley of death, commercialization value of death, or anyone knows words like the adoption value of death, or things like rejection. Rejection is what happens when they stop calling you back, right? It's like, yeah, they took your technology in for a little bit, then they stop calling you back. So we want to make sure that your technology is not rejected. In terms of track record, our organization has secured about $141 million of public money from the government of Canada over the last 18 years. And we've been able to leverage that with private sector follow-on investment to close to $500 million in follow-on investment. In terms of the ecosystem, and I think this is something that maybe Portugal can really take as a best practice, we have actually recognized that innovation doesn't happen on an island. You know, innovation happened in a bit of a village scenario where the village has to be there to raise a child. So we really believe that any innovation that you place in the middle of the circle needs this ecosystem approach to move it forward. And that's what we're doing. We are harnessing the collective strength of the ecosystem to move innovation forward in a faster way. Because this idea of doing things in silos seriously slows things down. And I think, you know, with the strategic response from the global pressures, we really need to take on that innovation, collaborative approach, ecosystem approach to move things forward in a way that makes more sense. In terms of our approach to innovation as an organization, we like to collaborate with the mine operators, small to mid-sized, large mining companies. And again, I mentioned we work with the startups, SMEs, SMBs, METS companies, and we offer innovation programming and funding as well to these companies. Overall, we like to do what we call, again, thought leadership in moving forward, and we like to be very global in our approach in terms of outreach, and we also like to secure those government relations that are important to move things forward. So, in essence, we're bridging the innovation gap. So I'm gonna go back now to the year 2022. In the year 2022, we realized that we needed to package our approach to innovation. So we wanted to find a mechanism to put in a box how we actually advance innovation. So we created an entity called MICA. So the logo you're seeing here with the different leaf part of the petals there, this is what we call MICA. And I'm gonna talk about MICA next. So MICA stands for Mining Innovation Commercialization Accelerator, MICA, another acronym. MICA is also a mineral, for those of you who know mining. But certainly, MICA is our vehicle to bridge the innovation gap. And what we did is over the last 4 years there, we got $45 million from the government of Canada, which we're now invested into a few different projects. And I'll talk about that in a moment. So again, the MICA network designed to modernize mining, strengthen the Canadian mineral and metal supply chain. And again, MICA connects the local, regional, national, and global innovation ecosystems. And I think this is really super important to recognize that your innovation that you're working on, your technology you're working on, exists within the context of this global, local, regional, national field, and you need to really understand who the players are that you need to connect with. When we started MICA, we looked at 4 technical areas: productivity, energy, smart, and environment. This is where mining has a problem, by the way, is in these 4 core areas. And again, we're moving into the critical mineral space, circularity, and also things to do with license to operate. That $45 million that I mentioned earlier on, we took that $45 million, put into 70 projects across the entire mining value chain. So we actually have technology projects all the way from prospecting to mine closure, and we'll be able to leverage that to over $250 million in follow-on investment. So we have been able to do what we call an 8 times multiplier of public sector investment, job creation, of course, pilot project, and commercial pilots that are in place right now. Our business model for MICA is with a membership model that takes into consideration all the different ecosystem players that play a role in the mining sector. And again, you know, we have 120 members across the mining value chain. Mine operators are part of it as well. We do a lot of activities across the mining value chain, across the country. We're going to mining in Durban next. We're in Brazil right now with the team. We go to Peru. We go to Germany, Aachen. We go to Balmar. And we also are very present in Chile and Peru and also in Argentina. So we're in various places where we are moving technology and innovation forward. Locally in Canada, we do have a footprint in every region in Canada, in British Columbia, Alberta, Calgary, for those of you who know Canada, Quebec, and also on the East Coast. So coast to coast, we have boots on the ground, sniffing out innovations that are coming out of the ecosystem. You know, one thing that I always say to Canadians is that we have too many secrets, too many technologies that we have that are sort of hidden in Canada, and so we flush them out through having boots on the ground everywhere. In terms of mine operators, we've got 6 mine operator members, access to the innovation teams, so we know what the problems are in mining operators, and we use our network to flush out solutions across the innovation ecosystem. These are some of the logos of the companies we're funding right now. You might know some of these companies, but these are all technology companies with demonstration-ready, pilot-ready projects that we're supporting right now. We have an associate partnership model where we're looking for friends. We're looking for friends, organizations that are like-minded, that we can partner with and connect with to move technology forward in a more systematic way. So here in Portugal, we're looking to connect with the different ecosystem players that have technologies, that have got memberships and technologies that we can access and move things forward. When we do project selections, we actually put project ideas in front of mine operators to have them give us their feedback. So every single project we fund actually has a home. So we're not just, pushing technologies to someone. We actually have this pool coming from within the industry. So we have a very comprehensive process that we use to select projects where they get ranked by the mine operators, and we have got this pool within the projects. In terms of our global outreach component, we are very active, again, I mentioned, in various countries. We have MOUs, alliance agreements with various players from across the world, and we do inbound missions and outbound missions to bring technologies to various places. We really believe in creating that soft landing platform for technologies. And I guess, that's something that we really value, is making sure that we create that runway for technologies from Canada to be able to safely land somewhere. So here in Portugal, we're looking for partners that we can work with to soft land technologies, not only for the purpose of helping you with your lithium mines and your tungsten mines, but more importantly, to bring technologies from Canada to Angola, to Mozambique, and to the other 4 countries that speak Portuguese that are part of the African continent. So we're very, very interested in working with the Portuguese ecosystem to bring these technologies to market over here. And again, in Canada, we do work with our trade commissioners, we do work with our embassies, in order to bring technologies forward in a very systematic way, in a way that actually uses the ecosystem. We don't believe in parachuting technologies from Canada onto a mine site. We really believe in taking an ecosystem approach in how we bring technologies to market from Canada to other countries. And I think that's how you get more buy-in, is if you actually partner with boots on the ground. There's a bit of a colonial mentality in just parachuting and flying over a technology. So I thank everybody for your time, and looking forward to any questions. If you have any questions for me specifically, you can scan the QR code here to get my number, my email address, and we can talk offline. Thank you very much for your time. Thank you.
Excellent. Thanks very much, Charles, and bang on time. The last 2 slots, we're going back to the start of the mining cycle, I guess, and going to look back at the exploration side of things. And the first up to look at exploration and some innovation in exploration is Arila, and she's going to talk to us about Minotaur.
Thank you very much. First of all, let me thank you, Arthur, and his team for actually inviting us to join all of our knowledge and providing the opportunity to actually exchange and engage with each other on commons that are of importance to all of us. I'm going to talk about a European project which has a really nice name. Is a Minotaur, is coming from actually ancient times, but in fact we are looking at the future. And Minotaur stands for Miniaturized Robotic Systems for Autonomous In-Site Exploration of Critical Raw Materials in Deep Land Deposits. Well, we heard over the last 2 days, and also you over the last 2 days, and also you as professionals, we hear a lot about the cost of ignoring the geological uncertainty, what that means for a business decision later on, but also for the geologist on the ground, but also for the actually optimizing the processing later on. So all of these issues together brought that we can summarize into some technical challenges, but also policy-related challenges. And the idea of the project was actually to tackle the multiple issues that are related with the geological exploration. What are the advanced in situ sensing methods we are using? Is it possible to use digital twin as well as artificial intelligence? How we can integrate that into a process? What are the new drilling techniques where actually we are working on? Or what are the geophysical and numerical modeling that we can actually use to optimize or to create a better information pool that help us to actually deliver on this? On the side of policymakers, we heard a lot the challenges related to the permitting. So all of the mining companies, they need a permit in order to do geological exploration activities. So there are a lot of hurdles on how you get these permits, the time it takes to get this permit. What is the public perception as well as the social acceptance of having these heavy machineries on site that do some drilling and also collect these cores? Who owns the data, how you integrate this new knowledge created with a use strategy as well as funding, but also ethical consideration. We heard a lot about social license to operate and also the social acceptance of the mining sector. So to actually tackle these challenges or to actually challenge the traditional way of doing exploration and drilling work, and to tackle what are the traditional inefficiencies that are observed from conventional drilling spreadsheets, the environmental impact, but also on the need of the sector to be as innovative as possible in order to actually provide solutions to mining companies, but also address the challenges created or seen by our sector or by the society as such. But at the same time, the idea is also what are the policy challenges, how we can actually address them or how we can create or overcome the permitting issues, but also the systems we put in place in order to have more ethical operations. So the consortium was born and is led under the leadership of the Luleå University, and we have the Technical University of Denmark, IMA, Industrial Minerals Association is on board, the University of Technico is on board, the Wrocław University, Patras, CFI, and also Ternamag. These are the partners of the consortium. As you can see, they are spread around Europe. And when these partners brought their minds together, the idea is let's see where we stand right now and where we'd like to go in the next steps. So what industry is doing right now that is working, and what are the areas where we need these new robotic explorers to be developed, and how we can create this drilling system which allows to actually advance the knowledge we have on a possible future deposit by using sensor technologies or in situ geological computation, which provides the new information to create a digital twin technology that helps to create the new geomodels and also the digital drill collars that can help us to make faster and quicker decisions. In here you can see the work plan. I'll not go into the details of it. All European projects will need to develop one, but in here you can see how the different developments by different working packages, they are actually interlinked together. And the concept of the Minotaur project is, as you can see in the photo, in the lower part of the photo you can see the deposit as with some knowledge we have right now, And thanks to this new Minotaur robot, the idea is to create a digital twin that is actually a reflection of the reality on the ground. And the idea is to also go in deep drilling, but also on horizontal drilling, but also contour drilling. So these were some of the specific challenges that we are working with the partners to be actually addressed. When we speak about the concept of this robotic explorer, the idea or some of the constraints or some of the opportunities we had is to create this modular approach, which is going to actually create the module to allow the robot to be operational underground, but also to see what are the inner and outer diameter in order to make sure that there is a smooth flow as much as possible, but also to allow the drilled materials to be or collected or to be stored on site. And to develop this 3D printed prototype by using electric action in order to see a bit how this robot is going to deliver relevant information for the geologist team. So by introducing the Minotaur team, I have also a call for you to see if you are still following the presentation. If you like to be one of the test sites, we have already a few volunteers, but if you like to be one of the test sites that would like to test this technology, don't hesitate to reach out, and then we can see whether it is possible. And with this, I know that the most precious of commodity is time. I'll give you 2 more minutes extra from my side. Thank you very much.
Thank you very much. Yes, well, hopefully that gets us a couple of minutes for questions at the end, because I've certainly got a couple based on that very short presentation. Last technical talk of the day before we have the closeout by the Deputy Minister. We're going to ask Philippa to talk us through, for those of you who've been around for the last 2 days, effectively now Spot Mine have actually had a stand-up, so hopefully you've had a chance to maybe meet and talk to them, but this is Philippa's opportunity to just give us a bit more detail on exactly what the project looks like.
Hi, my name is Philippa, and I'm an exploration geologist at Spot Mine, an exploration consulting company. I would like to present MineSpot, that is an innovation project co-financed by Compete 2030, Portugal 2030, and the European Union. With this project, Spot Mine aims to focus on innovation on the early stages of mineral exploration, with the goals of speeding up the exploration process. So a little about us. Spot Mine is a startup, a Portuguese startup, and we are formed by former members of the University of Porto. Our mission is to transform scientific knowledge into innovation solutions to accelerate the mineral exploration for the mining sector. Here you can see our multidisciplinary team. We have geology, with geochemistry, geophysics, remote sensing, and also artificial intelligence. While in academia, we had the opportunity to participate in several projects, and international, like for example, S34I, Green Peg, and LIGHTS, and national ones such as Flapsys, Cavalli, and Innov Mineral. While we were on these projects and while we were in academia, we also authored multiple papers, most of them focused on lithium exploration, but also in other critical raw materials. In these projects, our expertise also involved with the access to different equipments and software, such as, for example, a spectroradiometer that we use to build our own spectral library on lithium minerals. And for example, a LIBS, a portable LIBS, that we calibrated ourselves with samples from Portugal on lithium minerals, petalite and spodumene ones. And during these projects, we were also able to have helicopter flights for radiometry that we use to compare with ground-based radiometry. While we were in the university, we were also able to build a network of collaborators and partners that were essential in building our startup. So, the European challenge. As we know, now more than ever, Europe has recognized its need for independence on a resources level. And we align with these goals. So, with the critical raw materials goals, as we have been speaking here in MINEX. For example, the idea of, by 2030, having 10% of the European annual consumption on critical raw materials secured, or of reducing the dependence on single third countries to 65%. So our main expertise that we have been developing is in lithium, as I've been talking about, but also other critical raw materials. And lithium, as we can see here on the first image, there's a lot of it in Portugal, although some people think there isn't. And we have a picture here of an outcrop where we can see spodumene. And spodumene is a lithium ore. And we have many pegmatites. That's the type of rock, the source where we can find lithium. Because here in this map in Europe, we can see that different sources of lithium can happen in Europe, like pegmatites, grayson, rare metal granites, or even hydrothermal or sedimentary. So here in Portugal, lithium is in pegmatites. And lithium is essential for the energy transition. And right now, also for batteries and for the renewable energies. So I hope that Portugal can help Europe to have a secure place to obtain this type of resources. So our response to this challenge was the MineSpot project. This project was basically what allowed us to start up. And our case study is here in Portugal, in an area well known for its lithium potential in the north of Portugal, and where we want to test our ideas and methodologies. And basically, the MineSpot project can be divided into main approaches. One that is using satellite data together with drone data integrated through artificial intelligence to produce 2D surface predictive maps of lithium occurrences. And the other one is to do 3D modeling. And for that, we are going to use 3D modeling, but before the drilling phase. That's the innovation here, is to try to do 3D modeling that then can guide the drilling phase. And for that, what we will use is DGPR, Deep Ground Penetrating Radar, together with field surface data, so mapping, to produce this type of models that can model the lithium ore underground. Now I'm going to talk a little bit about the general methodology of the project. And here we can see we have activity 2 and activity 3 that are A2 and A3. A2 is the phase of collecting the satellite data. A3 is the drone collecting data. And for the A2, the satellite one, we will focus on obtaining data from LSAR and also SWIR, shortwave infrared, and from the drone, LiDAR, thermal infrared, and radiometry. The A4, the activity 4, is integrating all these sources of data, different sources of data, together using artificial intelligence in predictive mapping for the lithium occurrences. Activity 5 is the 3D modeling, where we will test the DGPR, and we'll use also the LiDAR and other surface data, the mapping that we'll be doing in the field. The A6 is our validation activity, and so for that we will use our specialized knowledge local historical data, in-field observations, so we are going to the targets, and also in situ analysis. So for that, we will also use portable equipments such as LIB, laser-induced breakdown spectroscopy, I already talked about that, and also XRF, X-ray fluorescence equipment. Oh, sorry. The A7 is a dissemination activity, and we will share our results through our websites, social media, conferences like this one, and papers. Here we have a simple illustration showing how our project will work. So typically, a mining exploration project takes up to around 3 years to reach the drilling phase. So MineSpot aims to reduce that timeline for 1 year and reach that phase in 2 years. And for example, here we can see the 2D predictive maps, like an example of what we intend to create, using the satellite and drone data. We can also see the DGPR to do the 3D modeling, and the field observations and the chemical analysis with portable equipment in the field. So our project is 24 months long. We are in the 6 months right now, and this was the first result that we obtained only using satellite data. So we call this the MVP, the minimum volume product. So in only 2 months, we only with satellite data, hyperspectral and multispectral, were able to obtain a map like this that has the zones with the most chances of having lithium occurrences. And since it's an area that we already know, because we have a lot of work in there, it's working because those areas are really pegmatites with lithium. So, for example, for this mapping, we use 4 inputs and 3 spectral signatures. One was spodumene in hand sample, another one was spodumene in an outcrop, and third one was the spectrum from the satellite data that could indicate lithium minerals. This was also put together with the fault structures from the geological mapping of 1 to 50,000 scale. So MineSpot is only the beginning. So we are starting in Portugal, but lithium and Portugal are only for this project, for the beginning, but afterwards we want to go to other critical raw materials, for example, rare earths, that we are already have some projects starting working on that, and also to other places of the world. For now, we are going to Brazil and Mozambique. Then we have plans to go to other places of Europe, like Spain, France, Sweden, Norway, and afterwards to go to the rest of the world, but start with Canada, that we already have connections there, and the United States. About our services. Although MineSpot is focusing on mineral exploration, that is our main expertise, our knowledge also allowed us to offer other services. And for example, environmental monitoring, using remote sensing, geophysics, geochemistry. We can also do field work. We can also build GIS databases and do 3D modeling. So thank you. I hope you had the chance to visit our stand earlier here in MINEX. You can find us at Facebook, LinkedIn, and other social media. We have our website. You can send us an email. And if you want, you can visit us here in Portugal, in Porto, in the north, near downtown. Thank you.
Thank you very much. We are up against time. I'm looking to see if we have any. I'm looking for Arthur to chase us off the stage, but I don't see him at the moment. I'm getting a thumbs up. Yes. Okay. If we do have questions for the speakers from this last panel, I'm hoping most of you will be attending the dinner. So please carry on the conversations at dinner, or I assume there's going to be time for a drink before we actually head off on the buses. So please, just one last round of applause. Thank you very much for our panelists today.